Okay, so welcome everyone. This is 15-251, just in case you're in the wrong class. So this class will be run by the following people. John Lafferty is teaching with me, so John and I will be divvying up the lectures between us. There are three TAs we have. We have Albert Chu. Is Albert around? No. Todd Phillips, who's sitting at the back. You guys might as well look at your, relief crew. Figure out who are the guys who are going to save you when things get tough. And Andreas Krause, who's not in town but will be back this weekend, so you'll see him next week, I'm sure. Okay. The web page is tilde15251. Go to the web page regularly. We'll post all kinds of random announcements on this, like your homework due date has been extended by a day, so you can breathe normally, or things like that. There's a class B-board as well, and actually the web page tells you how to access the B-board in case you don't know how to access it. Most of this information should be in the course document that you just got. So if you don't get all this, the slides will all be on the web page, will be all on the website, so you should be able to access them as and when you want. So you can review them, figure out what's good, what's bad, what you understand and what you don't. But do check both these resources regularly. Okay. Do read the course document. It contains a whole bunch of information that, over the years we've figured out what kind of questions you guys face, and we've put the answers to most of them in the course document. So read it carefully. One of the things you'll notice in the course document is the breakdown of your grade, your final grade. And I'm sure you don't want to think about it right now, but might as well, mention it right up front. There are going to be 12 homeworks. In fact, the website has this detailed calendar. It tells you when the homeworks are going to go out and when they are due, so you can plan your life accordingly. There are 12 homeworks. They count for 35% of your grade. There are 3 in-recitation tests. In fact, the calendar will tell you when these tests are. They count for 30%. In-class quizzes 5%. The final is 30%. The lowest homework grade is going to be dropped. So you don't need to worry about one homework. Maybe you bomb one homework, that's fine. The lowest test grade is worth half. Okay? Everybody is happy with that. So in case you do understand that, you can do a little pop quiz right now. If Susie gets blah and blah blah and blah in her tests, remember, the lowest test grade is worth half. Answers?
80.
So it's 80 out of 30%.
Oh, okay.
So it's, you half your lowest grade, you add the other 2, and then you suitably normalize, and you get 24. In case you aren't happy with this, you can look at this offline and figure out how much Susie will get. Okay, so that's what your grade's going to consist of. Homeworks are like clockwork. Every Tuesday the homework goes out. Next Tuesday the homework's due. Okay, except for a couple of homeworks which are 2 weeks long. Most homeworks are a week long. You can, we figured out that, there are times when you need that one extra day or 2 extra days. You have a test, some other commitments. So we allow you to submit homeworks late, but it's not without a price. So for every day that you submit homework late, we'll take off 7 points. Okay. Each homework is going to be worth 100 points, by the way. Okay. So we take off 7 points for every day. And we can do this you can only delay it 7 days, so you can submit it up to 7 days late, 49 points off. On the 8th day, you basically give up on the homework. Okay, so you get 0 on that. Okay, all written homework solutions should be submitted as PDF files. If you don't know how to create PDF files, look at the website. And the course document tells you where and how to submit your homeworks. So read it carefully. Homework number 1 is going to be out today. It'll, we don't waste any time. So homework 1 is going to be out today, due in a week. Have a look. Okay? Oh yeah, if you have any questions, please ask. That's the rule of this class. If I hear silence, I assume that you guys are totally with me. Okay? So there's something we're trying this semester. These are extra credit tokens. So there are going to be some problems. These are extra credit problems. If you solve them, you get a token. A token is worth something. It's either worth one problem, worth up to 20 points, on some subsequent assignment. Okay? Or you can use it to buy off up to 3 late days on a future assignment. Okay? People happy? So you have to tell us explicitly when you're using your token. So for instance, if you're using option A, you should write on your homework, I haven't done problem 2 because I'm using my token. And the problem's worth less than 20 points, I'm using 1 token, so I'm fine. You'll get full credit on that problem. Okay. Or you can submit a homework late, but no more than 7 days late. So we aren't saying, you can submit it 10 days late and say, oh, I'll just take the 7 days penalty plus 3 days of token credit. No. 7 days late is 7 days late. And if you're n days late and you use 1 token, you are n minus, we'll reimburse you n minus 3 points, n minus 3 times 7 points. Okay? So this is all elementary arithmetic, you can figure it out. I won't belabor the point. Any clarifications? Yeah?
Let's say you submit 1 day late, you get 14 additional.
No. There are no loopholes. That's the bottom line. If it sounds like you're getting something for nothing, you aren't. Okay. One of the more sort of unpleasant slides of this talk is, some of you are unclear about how much you can collaborate, and the course document gives a lengthy list of things you can and can't do. We want you to collaborate because some of the problem sets are hard, and they're designed to be hard. They're designed to challenge you, and we want you to think. And thinking often comes best in pairs, in groups of, in small groups. So if you're working with somebody else, you can bounce an idea off, and they say, no, that's a really dumb idea, and here's why. And you come to an idea much faster if you're working in groups, we feel. However, each person should get his or her share of the credit. So what you have to do is you have to write down your assignment yourself. You may not share written work. You can work in pairs, you can work in groups, you can exchange ideas, but then you have to go off to your room, to the clusters, and write up the solution yourself. Okay? You also may not use Google or other web resources or solutions to previous year's homeworks. Many of our problems, over the years we have tried and tested a lot of problems. We've debugged them. We know which problems are good, and some of them are real gems. And we'll try to give them to you, but that does mean that the solutions are out there. In fact, nowadays the solution to everything's out there. You just go to Google, you ask, if you don't get an answer, it doesn't exist out there. So you want to be careful. You don't want to ask Google the answer to your questions. Yeah.
Can we use Google as a calculator?
You can use Google as a calculator. In fact, you can use a calculator for that matter. It's though in most cases you won't need to use a calculator. On the last page of the course document is an honor code. You should read it carefully, and you should sign it, and you should return it to us. And in fact, on your first homework assignment, you'll notice that we'll give you 10 points for doing two things. The first one is that you should mention who are the people you collaborate with. That's a requirement that we have in the Honor Code. And the second thing is you should sign and you should give us back this sheet. And for both these things, we'll give you 10 points. And this is not to just give you free points. This is to illustrate how importantly we take questions of collaboration and cheating. And I notice several of you are already signing it. Just read it before you sign it. You got to be careful about these things. I might have just taken your firstborn by asking you to sign on the dotted line. Okay. So textbooks. There is no textbook for this class, which means that it'll help you a lot if you come to class. If you come to the lectures, you'll get a lot more out of the course than if you don't. So we don't make it mandatory, and we try to put as much information as we can on the website. But there is some stuff that we can somehow impart only in lectures, and perhaps clarify only in lectures. So we do encourage you to come to lectures. But most of the resources, most of the information, handouts and stuff like that will be on the website, and you'll be able to access them. Okay. Feel free to ask questions. The course is designed to work best in an interactive setting, and ask questions. If I don't know the answer, I'll find it out. Okay. Any questions? Cool. Okay, so let's begin, and this lecture comes with gadgets. And just so that you know, I don't even know how to make pancakes, but here goes. Okay, so actually, where's my... Whoops. Okay, so the problem is this. The chef at our pancake shop he's sloppy. So he makes all these pancakes, and the pancakes are of different sizes, and he just stacks them up like so, right? Some of the pancakes are bigger, and some of them are smaller, and he just stacks them up. But on the other hand, the waiter, when he delivers them to the customer, he wants to, get the best tip. He wants for it to look the best. So he wants it so that all the pancakes are sorted. The largest one at the bottom, then the second largest one, something like this. Much more aesthetically pleasing, right? But, the chef gives it to him, and our waiter doesn't want to use his hand, right? So what he does is that if the thing looks like this, he has a spatula. So he puts the spatula in, and then he flips it. Okay? So you got some number of pancakes, and maybe the whole thing looks like this. He puts the spatula in, and he flips it. Okay? So you're starting off with a stack of pancakes. And you want to end up with a stack of pancakes that's all sorted. The smallest one on the top, the largest one on the bottom. And of course, every time you flip, there's the danger that something's going to fall down, or something's going to break, or, it's cooling off fast. And you want to do this as fast as you can. So the question is, how fast can you sort pancakes? So if I were to start off with some number of pancakes like this, and I were to ask you, well, how am I going to sort this stack of pancakes? Can you guys see this? Well, maybe you can't, so maybe I should put them just for illustration purposes. Please don't try this at home. So I've laid them out. I've changed the representation of the problem, right? And now I'm asking, how will you sort these pancakes? So how would you sort these pancakes? Yeah.
First, when you flip them, you have to make sure to get the biggest and the bottom first.
Okay.
That's out of the problem.
So if I want to flip all of them, then I'll have to, it was stacked up like this. I flip it like this. I move them back.
Right.
And that's, so just right off the bat, you realize this is so inefficient. I'm trying to deal with these 5 pancakes out here. This representation, even though it's very clean, it's very inefficient for me, for you to describe what's happening. So let's develop a representation that will make life easy for us. Let's start off with the sequence of pancakes that we had. That's the one on the top. This is the one on the bottom. And let's just make life easy for ourselves by giving them numbers. Numbers 1 through 5. 5 for the largest pancake, 1 for the smallest one. And let's even just, get rid of all the other notation and just write it as this. That's a stack of 5 pancakes, the tallest one, the biggest one on the top, the smallest one on the bottom. That's 5 pancakes right there. Okay? And it doesn't quite look like that, but maybe I should change. No, forget it. Don't worry about it. So this is the stack of pancakes that I want to sort. What's the smallest number of flips I would need to sort the stack? So one thing you'll realize in this course is it always helps to have a piece of paper and a pencil in your hand. So most of you have it already. So take out your papers and pencils and figure out what's the fewest number of flips you can do in order to sort the stack of pancakes, and we'll maybe give it a minute or two. Okay, answers. 5, 4. Do I hear 3? 3? No. 4, 5. Okay, so somebody who said 5. Now nobody raised their hands because somebody said 4. Okay, 5. Let's go for it. How would you sort? Say it again.
Okay, so my way of doing it was to flip the largest pancake to the top and then flip the whole stack, so that you get the well, I guess the second place. So I was Flip it once, the whole stack.
Flip it once, the whole stack. So this gives me 1, 4, 3, 2, 5, right?
So now you want to flip it so 4's on top.
Okay, so let's flip it so the 4's on top. This gives me 4, 1, 3, 2, 5.
Now flip it so 4's on top of 5.
So I flip this whole thing, right?
Yep.
So this makes it 5, 4, 1, 3, 2.
Now flip it so 3's on top.
3, 2. That's 5 flips. Can anybody do 4? Okay, go ahead. 5, 2, 3, 4, 1.
Flip,
Right?
starting the 4.
Flip starting the 4.
Yeah.
Okay. So that's 4, 3, 2, 5, 1.
And then flip starting the 2.
Flip starting the 2. So that's 2, 3, 4, 5, 1.
And then flip the 5.
5, 4, 3, 2, 1.
And then flip.
So you can actually do it in 4. Can you do it in 3? Yeah. So that's the question, right? Can you do it in 3? So anyways, you could do it in 4, and in fact there are several ways of doing it in 4. Here was one where we flipped the top 4 pancakes to start off. And here's another way in which you flip all 5 to start off. Then you flip this, then you flip the top 3, you flip the top 4 again, and there you have it. So there are several ways in which you can do 4. But what's the best way to sort these pancakes? So very often in the class it will help for us to make things concrete, give things names. And one of the things that we'll do right off the bat is we'll say, well, let x be the smallest number of flips required to sort this guy out here, this stack of 5 pancakes. Okay? So x is just a name, it's just this quantity that we want to figure out what it is. And we want to give both upper and lower bounds. And what we've just done is given what? We've said that x is going to be at most 4. It takes at most 4 flips to sort this stack. And when we ask, can we do it in 3, we are essentially asking ourselves, what's the lower bound? Is the lower bound 3? Is the lower bound 4? Is the lower bound 2? Which means, can the upper bound be reduced? We're trying to, there's this quantity out here, and we're trying to approach it from both sides. We're trying to localize it as much as we can. And in fact, what we'll be able to prove is we'll be able to prove that 4 flips are actually necessary. Okay? And here's a proof. So the proof says, suppose 3 flips were needed. Okay? That's just 3 flips we have with us. Then flip number 1. Might as well put 5 on the bottom. Why? Well, suppose it doesn't. Then flip number 1 puts 5 somewhere in the middle. The only way to get it to the bottom, eventually 5 will have to be at the bottom. And the only way to get it at the bottom will be to bring it to the top once again. Okay? The only way to get anything to the bottom is for it to be at the top in the previous step. Are you guys happy with that?
Yeah.
Yeah, good. So in that case, 5 would go somewhere into the middle, it would have to come back to the top, and then it would go to the bottom. That's 3 steps right there, and we haven't even taken care of the rest of the mess we have out there. So we would have used up our 3 steps just to get 5 to the bottom. So might as well put 5 to the bottom right away. Does that make sense? So after the first step, it looks like that. Now the claim is that flip 2 must bring 4 to the top. Because remember, 4 has to go somewhere out here. And for it to go somewhere out there, it better come to the top. Okay? So flip 2 might as well bring 4 to the top. If it didn't, then again we would be spending more than 3 flips. So our first 2 flips are essentially forced. Which means after the first 2 flips, we must look like this. We've flipped 5 to the bottom, we've got 4 to the top. But there is no one single flip which is going to sort this. Okay? Hence it's not possible to finish with flip 3, and hence 4 flips must be required. Yeah?
But the one you did, the second flip didn't put the 4 on the top.
The second flip did put the 4 on the top.
Like the one you did with the 4 steps.
That's right. So what did the argument say? The argument said, suppose there was a way. That's an excellent question. So the question out there is, the sequence of flips that we did to sort the stack of pancakes, in the second flip we didn't bring 4 to the top. That was your question, right? Absolutely. And that's totally correct. What this argument is doing is it's assuming that suppose 3 flips were possible. It's an argument which proceeds by contradiction. You first assume, suppose 3 flips were possible. And then at the end of it, you derive the fact that if 3 flips were possible, there is no way to sort this thing in 3 flips. And say that again?
Using that argument, this would also prove that 4 flips are insufficient.
This would also, so right at the sort of beginning, suppose I said, suppose 4 flips sufficed. Then the first argument still holds true. We might as well bring 5 to the bottom. But the second step doesn't hold. It's not necessary that we'll have to bring 4 to the top. Okay? So the argument proceeded by saying, suppose 3 flips were possible, then our first 2 actions must be forced. Our first 2 actions must be bring 5 to the bottom and bring 4 to the top. But then in that case you can't sort it in 3. And hence 3 flips cannot be possible. We derived a contradiction at the end. Did that make sense? Questions? So what we have is we have what we call a tight bound, a matching upper and lower bound of 4, and we know that x, the quantity we were looking for, is 4. That is 4 flips were required, and we could do it in 4 flips. Okay? Yeah?
Why is upper bound 4?
Because we just gave a sequence that sorted it in 4 flips.
X could be greater than 4 flips.
Say that again?
It can be more than 4 steps.
Absolutely. But what we are looking for is, we are saying x is the best way. So we are defining x to be the best way to sort this. And we'll come back to this question in just a moment. But we might as well, rejoice in the fact that we've proved our first theorem. And our first theorem says we can sort this stack in 4 flips. And this is the best we can do. Yeah?
So if we could solve in 3, would the upper and lower bound both be 3 then?
If we could solve it in 3, and if we could show a lower bound of 3, then the upper and lower bounds would be 3. And you'll see an instance of that in just a moment. Okay. So having been able to stack this particular, sort this particular stack in 4 flips, the natural question that we ask are these questions. Can every stack of 5 pancakes be sorted in 4 flips? Or does there exist a 5 stack that requires 5 flips? What do you guys think? Which one's correct? How many for the second one? How many for the first one? No. So I'm asking, can every stack of 5 pancakes be sorted in 4 flips? Or is there a stack of pancakes which requires 5 flips? So since there was an overwhelming majority speaking up a second, yeah?
Alright. Let's try to solve one of those, solve the other one.
Absolutely. So if one of them is correct, the other one's wrong. That's why you can only vote for one of the 2. Which one do you vote for? Okay. And how would you prove it? Don't know. That's fine. Hey.
I would say this because in the previous one with 1, 4, 2, 5, there is a run of like 2, 3, 4. So if you make that less ordered, then
Hold that thought. We'll come to that in a moment. So in general, these are the kind of questions we ask in our discipline. So one of the aims of 251 is going to be, this course used to be called How to Think Like a Computer Scientist. And then it changed to 10 great theoretical ideas, and then it changed to great theoretical ideas in computer science. And we are getting to a more, more fair and balanced definition of this course. But in general, what we are trying to do is we are trying to figure out how does a computer scientist think? And these are the kind of questions that you'll have to ask yourselves again and again during your study of 4 years out here. But in general, the question you're asking is, how difficult can the cook make things for the waiter? So here's an image that's really useful to keep in your mind when dealing with problems in almost all of computer science. Is you got to think of there being 2 adversaries. You got to think of this drama going on in the kitchen, where the cook and the waiter, they have nothing to do. It's really it's a totally run down place, and the cook and the waiter, they just all day they just scheme and connive. They hate each other's guts. So the cook wants to make life really miserable for the waiter, but the waiter wants to do as best as possible. He really likes those tips. So the cook is trying to figure out the worst possible stack, knowing that the waiter is going to do really well. If there is a way to sort it in 4, he'll sort it in 4. And the cook's trying to figure out, how bad can I make it for the waiter? And the waiter is saying, I just want to do as best as possible. And in fact, when you do your algorithms courses, your program will be given an input. And you will say, no matter what input I get, I want to do as good as possible. And you should think of an adversary sitting there saying, aha, I should give this program the worst possible input. And that's exactly what's happening here, but I'm jumping ahead of myself. Think of this in terms of 2 adversaries. Or think of it this way. Here's another way of viewing exactly the same thing. Let's define something called the fifth pancake number. 5 pancakes, the fifth pancake number. The fifth pancake number, P sub 5, is the least number of flips required in the worst case. No matter how mean the cook is, I should be able to solve it. I should be able to sort the stack in P sub 5 number of flips. Okay. And I want to give upper and lower bounds for this. Okay. And what we know is that if the cook was mean and he gave that stack of pancakes that we got, that we had initially to start off with, 5, 2, 1, 4, 3 or whatever it was, then the cook can force us to make 4 flips. You guys agree? Disagree? The cook can force us to make 4 flips. What do we know about this? Nothing. We don't know whether there is, how many flips will it take to sort the worst case. This is a question, comment, something.
In investigation yesterday, we did something like breaking chocolate.
Uh-huh.
And this is where it seems complicated like it. Because there's only 4 spots where you dip them.
Okay. So, can you give me some way so that, can you tell me in at most 10 flips, I'll be able to sort any stack that you can. Yes, no?
Yeah.
Yes.
Okay. Yeah, because you.
You
Go
can
ahead.
always bring the highest number left to the top and then to the bottom.
Good.
And so there's 5, so that's 10.
Awesome. So you can always sort it in 10 flips. Just loosely speaking, you can sort it in 10 flips. Wherever 5 is, bring it to the top, then bring it to the bottom. Okay? Now you've taken care of 5. 5's at the bottom, where it should be. Then bring 4 to the top and bring it to the bottom, just above 5. There are 10 pancakes. There are 5 pancakes. Each one takes at most 2 turns. That's 10. Excellent. So we can say something out here. We can say P5 is at most 10. Once 2 sorted. So the argument out there was, well, actually you really need to care about 5, 4, 3, 2. If 2 is in the right place, 1's in the right place. Right? So in that case, you can actually make this 8. Maybe you can do better. We'll come to that. Just 1 second. So just, don't mean to belabor this analogy of what's the worst case. So in the worst case, the fifth pancake number is just saying, take every stack. So the cook, he thinks of every possible stack. And you'll see soon that, there are 120 stacks. In fact, all of you have done concepts. 5 factorial is 120. And there are 120 stacks. 120 possible stacks. And for each one, there's a number associated with it, which is the least number of flips the waiter can do to sort that stack. So if the first stack was that one, then that number is 0, right? It's already sorted. We just did that, right? It's 4. Okay? And P5 says, look at all possible stacks. And look at the one with the largest number under it. This number is represents the performance of the waiter if he's doing his best. And by picking the largest number, you're just saying that the cook is really mean. He wants to make the waiter suffer as much as possible. Okay? So that's what the lower bound is saying. It's the least number of flips to solve the worst case stack of pancakes. And one thing to point out, our notion, our nomenclature out there, our use of words, is saying solve the worst case stack of pancakes. In this course, one of our objectives is going to be to help you do proofs. And one of the first steps in doing proofs is to be very precise about your use of words. The word "the" out there seems to indicate there's one. It's the worst case. But there might be several worst cases. So in general, it's a good idea to be careful about these things and to perhaps say a worst case stack of pancakes. Okay? It's useful to keep these things in mind. You'll return to this again and again. But now that we've defined Pn, Pn is if I have n pancakes, what's the best way to sort the worst case stack of n pancakes? So let's do since you have your paper and pencil ready, might as well do a few more little things. What's P sub 0? That's an easy one. P sub 1? 0. 1, there's one pancake, it's already sorted. What's 2? 1, because either the big one's on top of the little one, in which case you have to flip it. That's the worst case, right? What about 3? 2. Okay, so who said 2? Somebody said 2. How do you sort a stack of pancakes in 2? Any stack of 3 pancakes in 2. You'd have to show me how to sort every possible stack of pancakes, right? So how about this one? So I gave away the answer, but here's there are only 3 possible stacks of pancakes. In this case, this one. Can you do it in 3? Okay. Everybody can, but you might as well tell me how to do it in 3. Somebody, yeah. So 1, 3, 2, flip it below the 2. So that'll become 2, 3, 1. Fair enough. Can you prove that sorting this requires 3 flips? Yeah. Okay. Suppose I could do it in 2.
Yep. And it takes 2 to 3 at the bottom, 2 is the way out of place.
Okay. If I could do it in 2, then eventually I have to get 3 to the bottom. So just moving 3 to the top and then moving 3 to the bottom requires 2 flips. And if you just do that, you'll figure out that 1 and 2 are flipped over. So you can't do it in 2 flips, you require 3 flips. Hence, there exists a stack which requires 3 flips. But in fact, for every stack, you can do it in 3 flips. And it's exactly what you just mentioned. I can do any stack of 3 in 3 flips by bringing the 3 to the top. That's 1 flip. taking it to the bottom, that's 2 flips, and then 1 and 2 might be flipped over, so I just flip them right back. That's 3 flips. So in fact, P of 3 is exactly 3. Every stack can be sorted in 3, and there exists a stack which requires 3. So this one is saying P3 is at most 3. And essentially what we have here is we have a procedure, a recipe, an algorithm to sort any stack of 3 pancakes. What we had earlier was for 5 pancakes, we said you can sort it in 10 flips, in 8 flips. And we had an algorithm for that as well. Exactly the same algorithm, in fact. Bring the biggest to the top and then move it to the bottom. So upper bounds usually correspond to algorithms in this case. Lower bounds correspond to examples, particular instances. And what you're doing out here is you're trying to find the best, you're trying to bracket things as well as you can. And this is something that you'll do again and again in this course, even later on. There'll be some quantity which you don't quite understand, and you'll try to find the best upper bound and the best lower bound. And if you're lucky, they both will coincide, and then you know the answer. But in some cases, it's kind of tricky. Life's not so good. But in any case, let's go back to P-sub-n. And let's find upper and lower bounds for P-sub-n. If you have an upper bound, think about the lower bound. And let's again take a couple of minutes. And if you remember, a lower bound, for a lower bound you'll have to show me a stack of n pancakes which requires some number of flips. For an upper bound, you'll have to tell me how any stack of n pancakes can be sorted with that many flips. So yeah, let's take a couple of minutes and think about it. Hey John, is the I don't have internet. Oh, I don't have internet. Okay. Oh yeah, of course. No worries.
I'm gonna try to reboot. See if.
I think everybody's internet is down, so it must be something with the room.
Yeah. Go outside, see if I can get it.
John, don't talk.
Is Tn Pn minus 1 plus 2?
Is Pn minus 1 plus 2. So the simple answer is no, because P2 was 1 and P3 and P1 was 0. So that's not true in general.
I mean, like for n larger than 3.
So the answer to that is also no. But what's the thought?
Because let's just when n is let's say n is 3 is like that's the base case, right? And then when you go 4 pancakes, then you can end up with 4 on the bottom.
Okay.
With 2 flips at most.
Okay.
And then the rest may require 3 more flips.
Will require. So you're saying that if Pn is at most.
No, let's say n is 3, right?
Yeah.
And then n plus 1 is 4. So you're going to use 4 pancakes. And then you try to get the 4 to the bottom.
Okay. Mm-hmm.
That requires at most 2 flips. And then the pancakes that remain in the top,
Right.
it takes at most 3 flips.
So what you're saying is you would require at most 2 flips. So how do you infer that this stack of pancakes that you're left with will require 3 flips?
I mean, it could happen like...
Why don't you construct a counterexample?
Yeah.
Yeah.
For the upper bound,
Upper bound.
it's 2 times the quantity n minus 1.
So a proposed upper bound is 2 times the quantity n minus 1. Yes, no, better upper bounds. 2n minus 3. Anything better?
N minus n mod 2.
N upper bound, lower bound. N minus n mod 2. So if n is even, you're saying it's equal to n. Okay, so let's actually start easy. We'll come to your thing in 1 second. 2 quantity n minus 1.
Yeah.
How do you do it?
So, in the worst case, you can have, like you would with dry pancakes, you just have to bring it to the top.
Good. So you bring the biggest one to the top and then move it to the bottom, and you do this only n minus 1 times, right? Okay. So let's move ahead if PowerPoint is going to let me move ahead. The suspense is killing me. Good. So let's wait until PowerPoint. So let's continue our discussion. Twice n minus 1, and this just follows from the fact that there are n pancakes. I'll move the biggest one to the top, move it to the bottom, move the second biggest to the top, move it to the bottom right above the biggest one, and do this n minus 1 times, right? And if the biggest, second biggest, until the second smallest are in the right place, then the smallest one must be in the right place. And, okay. Good. Yeah.
Doesn't that depend on the algorithm to sort these pancakes? Like,
Absolutely. So you gave me an upper bound.
right, but that's just for my algorithm. You can see the stack of pancakes that would be better sorted.
So right.
Actually, ordering each one individually doesn't like a group that's switching that.
Right. So what I wanted was, I wanted some upper bound. And what you gave me was some upper bound. It might not be the best upper bound,
Yeah.
but you did give me some upper bound. You said in this algorithm, no matter what you do is not going to take more than twice n minus 1 flips. And that's totally true. But there might be a better algorithm lurking there. In fact, maybe his algorithm, which might be able to do even slightly better. So let's find out what your algorithm is. How do you get twice n minus 3?
We already proved that P3 was 3. So if you can always add another number, make n bigger by 1, you can always do 2 more steps.
Excellent. Go ahead.
Isn't it because when you get to the last 2 on the top, in the worst case, that's 1 flip as opposed to usually where it's 2.
Both the answers are in fact correct, and both of them are exactly the same. It's P1 is equal to 1. P2 is equal to 1. If you have 2, you just require 1 flip. Whereas this one would say P2 would be 2. So it just says, do the bring to top method. And when you are left with 2 pancakes at the top, either you're sorted or you just require 1 flip. So I think the computer might have died, in which case, hey Todd, can you help me with this one, please? You might just have to.
Something. See, I came down and then it worked.
Yeah. Well, it doesn't seem to be doing too much.
No.
And let's just. Okay. So we do all of us agree that twice n minus 2 and twice n minus 3 are both valid upper bounds for exactly the same algorithm, in fact. How about n minus n mod 2?
I realize.
Okay. Any lower bounds? Better upper bounds? Yeah. Okay.
Because for worst case, it would be that each pancake have to separate between each one. So it'll be at least n minus 1.
So a proposed lower bound is, let's look at the stack of pancakes. It may be, and we'll make this precise in just a moment, it may be the case that we might have to separate each consecutive pair. So imagine a situation where I gave you a stack of pancakes and you said, look at this stack of pancakes. Every pair of pancakes that are touching each other should not be touching each other in the final solution. Say 1 and 3 were touching each other. Oh, cool. And I can figure out. Oh, yeah. Oh, boy. So if you could come up with a stack of pancakes where every pair of pancakes that were touching each other will eventually not be touching each other in the final solution, you have to say, I have to separate these two guys with one move. So if there are n pancakes, there are n minus 1 places between the pancakes. So let me ask a question. Can you construct such an example? Go on.
For the 5 pancakes,
Sure.
if you had 5, 2, 4, 1, and 3. So all of the numbers don't are consecutive, the ones adjacent to it. So that makes it they have to split between
5, 2, 4, 1, 3. So between 5 and 2, you'll have to separate them. 2 and 4, 4 and 1, 1 and 3. So that requires at least 4. How about between 3 and the plate? Right? So in fact, the fact that 3 is resting on the plate means that you'll have to separate 3 from the plate at some point. So in fact, if you had a stack of pancakes where each consecutive pair would not be consecutive in the final solution, you would have to separate each one of them. Each one of them would require you to put the spatula there at least once. And that would be n.
It's not very happy.
Yeah. Okay. So
Hold on to it. Work.
Oh well, thanks, Stuart. Oh yeah, that'd be awesome. Okay, so suppose I wanted to look at n, and just for simplicity, let's say that n is even. Then how about the stack, which looks like 2, 4, 6, 8 till n, and then 1, 3, 5, 7 till n minus 1. Now in this stack, you'll notice that between every pair of consecutive pancakes, there's a gap. You would have to place the spatula somewhere there. So you'd have to put your spatula at least once between every pair, provided n was not equal to 2. If n was equal to 2, then 2 and 1 need not be separated, perhaps. Right? So for all n greater than, for all n greater than 2 and even, we know that P of n is at least n. How about odd n?
Put the odds on top.
Put the odds on top. So let's try this. 1, 3, 5 up to n, and then 2, 4 up to n minus 1, right? And this would work provided n was not equal to 3. Because if n were equal to 3, then 2 and 3 would be adjacent to each other and perhaps not need to be separated. So in fact, we can also say that for all n greater than 3, odd Pn is at least n. And we finally might as well use the fact we've already proved that P3 is equal to 3. So therefore, for n equals 3, Pn equals n. This just says, you can put this all together. It says that Pn is at least n, and is at most twice n minus 3 for all n greater than or equal to 3. This was the upper bound that you proposed. This is the lower bound that you proposed, right? Is everybody happy with this? This came with an algorithm, and we'll call this the move to top algorithm, just to make life easy in future discussions. There's a slight chance that this will come back up, but let's continue our discussion out here. So we know that that any stack of n pancakes can be sorted in 2n minus 3 flips and might require as many as n flips. And it's very interesting. So this problem actually came up. So, by the way, you might be wondering, what has this to do with anything that I'm going to do with the rest of my life, right? So, and it's a valid question. You should ask these questions every once in a while. Why the heck am I doing this? So, interestingly enough, these bounds were the best known initially. This was mentioned in a paper of a gentleman called Jacob Goodman, who wrote under the pseudonym that's Harry. And if you read that fast, it's supposed to be a pun on the fact that the waiter is harried. Joy and happiness. Okay. So, good. And let me try to send this to the screen. It might be my laptop, but let me try it once again.
Okay, dude, because I have the slides here, if you want. You think it's your laptop?
Yeah, probably. Let's try.
This is from Spring 05. So.
It should be okay. So this was proposed in a paper by Jacob Goodman. The next person to work on this, they were in a couple of, they improved this to about 5/3 of n plus something. I think. Hey John, do you
want to try this? Or do you want to try this?
Let me just quickly. Yeah, you'd think technology would help us, right? But okay. So they proved. There were two people who proved something like 7/6n and 5/3 n plus 5. The people who proved this, one was a guy called Gates, and another one was called Papadimitriou. This guy was a professor at Harvard, is now a distinguished professor at Berkeley. This guy runs a software company in Redmond. So it's kind of fun how it works out. You know, if you work on this problem, you'll probably be one of the richest men in the world, if not the richest. Well, I might as well mention that the next people who worked on this did not make $1 billion, so it's not a guaranteed thing. But why were they studying this? So the reason they were studying this was because they wanted to study. How do I get the screen? Okay, lights. Okay, so these bounds were given by these two guys. And it was subsequently improved to, the lower bound was improved to 15/14n. However, they were studying this because they wanted to study the so-called diameter of the pancake network. And why would you study something called the pancake network? So the reason for that is, and I'm cutting to the chase. If you don't know this, you'll learn this very soon in the counting lectures, that there are n factorial permutations on n elements. So 5 factorial was 120. So if you look at all possible stacks of 5 pancakes, there are 120 distinct stacks. So what you can do is you can define a network. Now, how is this network defined? For each node, And think of this network as a bunch of hosts and wires between hosts. These hosts we'll call nodes, and the wires we'll call edges. Okay? So each node will be assigned one of the n factorial stacks. It will be given a name, and this name will be one of the n factorial stacks. And you'll put a wire between two different nodes if the stack represented by one can be turned into the stack represented by the other by just one flip. So for instance, if n equals 3, 3 factorial 6, there are 6 nodes in this one. And note that if I take this stack, I can convert it into this stack by just flipping the whole thing over. Or I can convert it into this stack by just flipping the top two things. Okay? So I can add edges like this. And for n equals 3, the graph is very simple. For n equals 4, it gets a bit more complicated. It's like, there are little pieces out here which look exactly like the original 6-node link cycle, but there are other cycles going all over the place. The graph looks really, well connected, really mixed up. And in fact, one thing you'll be able to prove is that the maximum distance between any two nodes in this network is at most the pancake number, P of n. And one way to see this, actually, maybe it's in the remaining 5 minutes we'll do this. But okay, so let's do this thing. Okay, so this is what we knew. So from any stack, you could reach a sorted stack in P of n flips. How about going from a sorted stack to any stack? I say I want to end up with 5 on the top, then 4 below it, then 1, then 7, then 3, then 9. Now I give you some long list. But you start off with a sorted stack. Can you do it in less than P of n steps? Why? Why?
Because from that one you can always get to a sorted given.
So from that unsorted stack, you could get to the sorted stack in P of n. Now every time you did a flip, if you did the flip again, it would undo the flip. So you could just do the flips in reverse order, starting with the sorted stack, and you would get to the unsorted stack. Okay.
Is there a bijection?
There is indeed a bijection between all ways to get from any stack to a sorted stack and from sorted stack to any stack. Okay? So now suppose I gave you some weird stack and I asked you to get to some other weird stack. How many flips? 2 P of n at most, right? You could go from there to the sorted stack, and then from the sorted stack to this other stack that you wanted to get to. But you said P of n. What's the story? How do you get from any stack to any other stack in P of n? Okay. But you can. And in fact, this is another one of these tricks that you'll get really used to. It's just renaming. Suppose you started off with this stack and you wanted to end up at this stack, right? And the pancakes in this stack have the white numbers 4, 3, 5, 1, 2, whatever. Let's just just rename the pancakes to be 1, 2, 3, 4, 5. Okay? Now this renaming will cause some new names to be given to these pancakes out there. And just go from this sorted stack to this unsorted stack in P of n steps. That's it. So in fact, you can get from any stack to any other stack in P of n steps. Okay? And So this implies that since this is some stack and this is some other stack, getting from this stack to that stack will require at most P of n flips. And so the distance in this network is at most P of n. But the reason why these guys were studying it was because these networks have very good properties. These networks have the property that, if up to n minus 2 nodes, let's say somebody comes and just nukes them, just completely destroys them, the network will still be connected. Despite these n minus 2 nodes, any n minus 2 nodes, the adversary, the chef who's lurking in his kitchen, gets really angry and comes and breaks your pancake network, destroying n minus 2 nodes. But still your network will be connected. And it's pretty incredible considering if you look at any particular guy out here, he's connected to only n minus 1 other nodes. So if that chef could delete n minus 1 other nodes, this guy could be separated from the rest of the graph. But if he can delete only n minus 2, that little bit less, the network will still be connected, no matter what he does. So this network's a very reliable network, and it's, in fact, you can prove this. It requires a bit of work. It's proved in that paper that it's optimally reliable for the number of links that you put down. So if you have n links and some number of nodes, then this is the best you can do. You can be reliable only against n minus 2 failures. And this network is going to be reliable. So the pancake network kind of was useful, and it is an object of study, object worthy of study. But generally this idea of flipping things to sort is an idea which has broader ramifications. So here's something that you may or may not see in future classes. What happens is these kind of ideas are also used to study mutation distance. So there are some sequences. There's the genome associated with 2 different species. And what you might want to know is how many things have to change in going from this species to that species. So the way it looks like is, it looks like there's a long sequence of, what's the word for it? Yeah, there's a long DNA sequence, and it has 4 different kinds of bases, A, T, C, and G. And you want this long sequence. So this guy has some long sequence associated with it. This guy has some other long sequence. So this might be A, T, A, G, C, and this might have A, G, G, A, T. And you might ask, how do I get from this sequence to this sequence? And the way we believe these mutations take place is that this long strand, it gets snipped in 2 places. And then this piece in the middle can possibly turn around and attach to the 2 ends. So there's this long thread, snip it in 2 places, take this piece and turn it around. Another way to look at it is the famous 3-armed waiter problem, where the waiter actually has 2 spatulas. He lifts the first one, he lifts some piece of the top of the stack, takes this middle piece and flips it around, and then puts the top back. And if you think about it, it's exactly the same as taking this, snipping at 2 places and turning it around. And you can ask the question, what is the shortest way to get from that sequence to that sequence using just sorting by reversals? And this is considered a fairly accurate measure of distance, of how long back these 2 species differentiated from each other in the evolution chain. And there are various other kinds of notions that are associated with this. Perhaps it's a good point now to end, but with a sort of a high-level point we want to make, is that the reason why we are studying all this in this class, and the reason for studying most of the things that we'll do in this class, is going to give you a perspective on computational thinking. how to think like a computer scientist. And the goal of computer science, a lot of people believe it's the big problem in computer science is spam and web search, and that's not true. The goal of computer science is to make you think differently, to model the world around you, to figure out how best you can do things, and if you can't do things better, why not? What are upper bounds and what are lower bounds, and how to get matching ones. So this lecture was just to give you an idea of the kind of things we do. Even simple problems can have many applications. You can become a millionaire studying this problem. So please think about this. Check out the homework. Hand in the collaboration policy. And what we'll try to do is we'll try to put these study Bs in an idea of the kind of concepts we studied in this lecture. And it's for you to keep us honest and make sure that you demand from us these study Bs so that we can help you direct your thinking. Thank you.